Very good afternoon to one and all. Whether my screen is visible and can you hear me? Please let me know. You can comment in chat box. Great, great. Thank you. Okay. So in the morning lecture we have discussed the heat transfer through composite slab. Okay, and we have seen the derivation for heat transfer through composite wall. So initially in this lecture, we'll complete the write-up part and then we'll discuss two examples on this particular point, that is heat transfer through wall. Okay, so please draw this diagram. Draw this diagram for the composite wall. Okay, so composite wall is made up of three different materials. Okay, so wall A, wall B, wall C, and these three walls or three slabs having different thermal conductivities, that is K suffix A, K suffix B, and K suffix C. Individual thicknesses of these three different walls are L suffix A, L suffix B, L suffix C. Then left hand side surface is maintained at T1 degree Celsius temperature. Okay, so it is maintained at a T1 degree Celsius temperature, and right hand surface is maintained at T4 degree Celsius temperature. Okay, T4 degree Celsius temperature, and T1 is greater than T4. T1 is greater than T4, so that heat is flowing from left hand side surface to the right hand surface, left hand surface to the right hand surface, and the interference temperatures between A and B wall is T2, and interference temperature between B and C wall is T3. Okay, then in this case, if you draw the temperature profile or change in temperature with respect to the distance, then it will be in such a manner. Okay, it is straight line within the wall. Okay, within the single wall. Okay, it is straight line within the single wall. It is straight line within the single wall. And if you want to draw the electrical analogy for this composite wall, then it will be in this manner. Okay, electrical analogy for the composite wall. So heat is flowing from left side to right side, and left side surface is maintained at a T1 degree Celsius temperature, or wall A outer surface temperature is T1 degree Celsius, and wall A inner surface temperature is T2 degree Celsius temperature, is T2 degree Celsius, and heat flow through the wall A having thermal resistance of RTH suffix A, having thermal resistance of RTH suffix A. Okay. Wall B having wall B having left hand temperature T2 and right hand temperature T3. Batch बदलली का? T2 okay, and wall B having left hand temperature of a T2 and right hand temperature of a T3. Similar fashion, wall C is having left hand surface temperature is T3 and right hand surface temperature is T4. Okay, and RTHB is the thermal resistance for heat flow through wall B, and RTHC is the thermal resistance for the heat flow through wall C. Okay. Everyone draw this diagram. Okay. Then further, let 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 L suffix A, let L suffix A, comma L suffix B, L suffix B, let L suffix A, comma L suffix B, comma L suffix C, L suffix C is equal to thickness of slabs A comma B comma C respectively. Thickness of slabs A comma B comma C respectively. Next, K suffix A, K suffix A, K suffix A, comma K suffix B, K suffix B, K suffix B, comma K suffix C, K suffix C is equal to thermal conductivity is equal to thermal conductivity of material K suffix A comma K suffix B comma K suffix C is equal to thermal conductivity of material A comma B comma C, thermal conductivity of materials A comma B comma C respectively. Then T1 comma T4, T1 comma T4 is equal to surface temperatures. T1 comma T4 is equal to surface temperatures. And T2 comma T3 comma T3 is equal to T2 comma T3 is equal to interface temperatures. T2 comma T3 is equal to interface temperatures. T2 comma T3 is equal to interface temperatures. Important note, since the quantity of heat transmitted per unit time through each slab through each slab through each slab through each slab is same. Through each slab is same. Therefore, next line, therefore, from Fourier's law, therefore, from Fourier's law, we have, therefore, from Fourier's law, we have Q is equal to minus K multiplied by A multiplied by dt divided by dx. From Fourier's law, we have Q is equal to minus K multiplied by A multiplied by dt divided by dx. For slab A, heat transfer will be given as for slab A, Q is equal to K suffix A for slab A, Q is equal to K suffix A multiply by area capital A multiply by area capital A multiply by T1 minus T2 whole divided by L suffix A whole divided by L suffix A. Rearranging above equation in the form of a temperature difference. Okay, rearranging above equation in the form of a temperature difference, we'll get T1 minus T2 is equal to T1 minus T2 is equal to Q multiply by L suffix A Q multiply by L suffix A divided by whole divided by K suffix A multiply by area. K suffix A multiply by capital A. K suffix A multiply by capital A. Okay, equation number 1. Give it as a equation number 1. Okay. Similarly, for slab B, heat transfer is given as Q is equal to Q is equal to K suffix B multiply by area multiply by capital A multiply by T2 minus T3 whole divided by L suffix B Then further we have rearranged this equation as T2 minus T3, T2 minus T3, T2 minus T3 is equal to Q multiply by Q multiply by Q multiply by L suffix B, Q multiply by L suffix B divided by K suffix B multiply by area. Q multiply by L suffix B whole divided by K suffix B multiply by area. Similarly, for slab C or wall C, for slab C or wall C, heat transfer rate will be given as Q is equal to Q is equal to K suffix C multiply by area capital A multiply by T3 minus T4 whole divided by L suffix C. Q is equal to K suffix C multiply by A multiply by T3 minus T4 whole divided by L suffix C. In the next step, we have to rearrange this equation in the form of a temperature difference. So equation will becomes T3 minus T4 is equal to T3 minus T4 is equal to Q multiply by L suffix C, Q multiply by L suffix C, Q multiply by L suffix C whole divided by K suffix C multiply by area. Whole divided by K suffix C multiply by area. This is our equation number 3. Equation number 3. Equation number 3. Then next we have to add these three equations. Okay, adding equation 1, 2, 3. Adding equation 1, 2, 3. So addition in such a manner that left hand side added on one side, or that will be added on left side, and right hand side should be added on the right side only. Okay, out of these three equation. Okay, so that we have added left hand side, that is the addition of all the temperatures. Okay, and addition of remaining part on right side. Okay, so addition will be in such a manner that T1 minus T2 plus T2 minus T3 plus T3 minus T4 which is equal to Q multiply by L suffix A divided by K suffix A multiply by area. Q multiply by L suffix A divided by K suffix A multiply by area. Okay, plus Q multiply by L suffix B plus Q multiply by L suffix B divided by K suffix B multiply by area. Divided by K suffix B multiply by area. Plus Q multiply by L suffix C divided by K suffix C multiply by area. Divided by K suffix C multiply by area. Now here minus T2 plus T2 will be cancelled, minus T3 plus T3 will be cancelled, and remaining part will be only T1 minus T4. Okay, T1 minus T4. Remaining part will be T1 minus T4. T1 minus T4. T1 minus T4. Now from this part, Q is common. If you take Q outside the bracket, so the equation will become T1 minus T4 is equal to Q into bracket L suffix A, L suffix A divided by K suffix A, K suffix A multiply by area plus L suffix B, L suffix B divided by K suffix B multiply by area and plus L suffix C plus L suffix C divided by K suffix C multiply by area plus L suffix C divided by K suffix C multiply by area. Okay. Then we have to rearrange this equation in the form of a heat transfer rate. Okay. So we have converted this equation in the form of a Q. Okay. So Q is equal to so just we have shifted this bracket on the left side and we will get the equation in the form of a Q. Okay. So Q is equal to T1 minus T4. Q is equal to T1 minus T4 whole divided by T1 minus T4 whole divided by in bracket L suffix A whole divided by in bracket L suffix A divided by K suffix A multiply by area, L suffix A divided by K suffix A multiply by area plus L suffix B divided by K suffix B multiply by area plus L suffix C divided by K suffix C multiply by area Okay, so further we know that the thermal resistance will be given as L divided by K multiplied by area. Okay, so therefore as the RTHA, that is the thermal resistance offered by wall A for the heat transfer, will be equal to L suffix A divided by K suffix A multiplied by area, and RTH suffix B, that is thermal resistance offered by wall B, will be equal to L suffix B divided by K suffix B multiplied by area, and the last one, thermal resistance offered by the wall C, that is RTH suffix C will be equal to L suffix C divided by K suffix C multiplied by area. L suffix C divided by K suffix C multiplied by area. Therefore, we can write for this particular equation, we can write Q is equal to T1 minus T4. Q is equal to T1 minus T4. Q is equal to T1 minus T4 whole divided by T1 minus T4 whole divided by RTH A plus RTHB plus RTHC. Thermal resistance of A wall plus thermal resistance of B wall plus thermal resistance of C wall. RTHA plus RTHB plus RTHC. Getting everyone? Now, this is equation for heat transfer through three slabs. Write down. This is equation for heat transfer through three slabs. This is equation for heat transfer through three slabs. So how we can generalize this equation? Okay, sometimes there will be a 4 slabs, sometimes there will be 5 slabs, sometimes there will be 2 slabs. Okay, so how we should generalize this particular equation? So in that case, we have to consider if there are n number of slabs. Okay, if there are n number of slabs, then if there are n number of slabs, then Q is equal to Q is equal to Q is equal to Q is equal to in square bracket T1 minus T minus T1 minus T suffix n plus 1 T1 minus T suffix n plus 1 whole divided summation of L divided by K multiplied by A from 1 to n. Summation from 1 to n, that is total summation of all the resistance into bracket L divided by K multiplied by A. Okay, so this is the equation we have to consider in general for n number of slabs. Okay, in general for n number of slabs. So in case of a 2 slabs, we will get the 3 temperatures. Okay, in case of a 4 slabs, we will get 5 temperatures. In case of a 3 slabs, we will get 4 temperatures. Okay, so in that case, we have to take the subtraction of first temperature minus final temperature. Okay, to find out the total heat transfer through complete slab, through complete composite slab or through complete composite wall. If you want to find out the total heat transfer rate, so in that case, for the temperature in the numerator side, we have to take the temperature difference between initial temperature minus final temperature. Initial temperature minus final temperature. Okay, getting everyone? Whole divided by, and we have to divide by thermal resistance of each slab. Okay, thermal resistance of each slab. So summation from 1 to n of L divided by K multiplied by area. Okay, so this is thermal resistance. L divided by K multiplied by area is the thermal resistance offered by that particular slab. Okay, getting everyone? Is there any question, any doubt? Now next, okay, problem on composite wall or problem on wall of oblique slab. Problem on wall oblique slab. Okay, keep your calci with you. Problem number one. Problem number one. Write down the statement. Problem number one. Write down the statement. Consider a slab of thickness. Consider a slab of thickness L is equal to consider a slab of thickness L is equal to 0.25 meter. L is equal to 0.25 meter. One surface is kept at one surface of that particular slab. One surface is kept at 100 degrees Celsius. One surface is kept at 100 degrees Celsius, and other surface at 0 degrees Celsius, and other surface at 0 degrees Celsius, other surface at 0 degrees Celsius. Full stop. Determine the net heat flux. Determine the net heat flux across the slab. Determine the net heat flux across the slab. Across the slab. Full stop. If the slab is made from if the slab is made from if the slab is made from pure copper, if the slab is made from pure copper, full stop, thermal conductivity of copper, thermal conductivity of copper, thermal conductivity of copper may be taken as thermal conductivity of copper may be taken as 387.6, 387.6, 387.6, 387.6 watt per meter Kelvin. Thermal conductivity of copper may be taken as 387 watt per meter Kelvin. Okay. So please let me know whether this problem is of plain wall or composite wall. Okay. Please let me know whether this problem is for plain wall or composite wall. You can comment in the chat box. Plain wall, right? Okay. So this problem is related to the plain wall only, because only one slab is provided and only one slab thickness is provided. Okay. So that we have to solve this problem by using the plain wall concept. Okay. So given data is the thickness of wall is provided. Okay. And it is L is equal to 0.25 meter. So write down the given data. L is equal to 0.25 meter. Then one surface is maintained at 100 degrees Celsius. Okay. So T1 will be considered as 100 degrees Celsius. Okay. T1 will be considered as 100 degrees Celsius. And other surface is at 0 degrees Celsius. And other surface is at 0 degrees Celsius. So T2 will be considered as 0 degrees Celsius. T2 is equal to 0 degrees Celsius. Ready? And the thermal conductivity, the slab is made up of pure copper and its thermal conductivity is provided, and it is equal to 387 watt per meter degree Kelvin or degree Celsius. Okay. So thermal conductivity K for the copper is provided as K is equal to 387.6 watt per meter Kelvin. And what we have to find out? We have to find out the net heat flux across the slab. Okay. We have to find out the net heat flux across the slab. So heat flux means what? What is meant by heat flux? Heat transfer rate per unit area is called heat flux. Okay. We know that. We have discussed this point. Heat transfer rate per unit area is nothing but the heat flux. So heat transfer rate per unit area, which is equal to small q. Okay. Which is equal to small q. Small q is nothing but heat flux. Small q is nothing but heat flux. So q by a we need to determine. Okay. Q by a we need to determine, that is nothing but small q, which is called as the heat flux. Okay. So simply, first of all, you have to draw, for the understanding purpose, you need to draw this particular diagram. Okay. So general diagram for the heat conduction through plane wall and provide the temperatures and appropriate nomenclature for the thickness T1 where we have located the T1 temperature and where we have located the T2 temperature. Okay, so T1 is equal to 100 degrees Celsius and T2 is equal to 0 degrees Celsius. Okay, locate that temperature and draw this simple one-dimensional diagram for the wall. Okay, then we know that for the plane wall, how we are writing the heat transfer rate equation. So we know that it is equal to Q. Q is equal to K multiplied by A multiplied by T1 minus T2 divided by L. Okay. So Q is equal to K multiplied by A multiplied by T1 minus T2 divided by L, where K is the thermal conductivity, A is the perpendicular surface area, T1 is the temperature of initial phase and or left hand side surface, and T2 is the temperature of right hand surface. Okay, and where L is the thickness of that particular slab. L is the thickness of that particular slab. Further, we have to determine the Q by A, that is the heat flux uh, that we have to find out from this problem. So for that reason, we have to transfer the A, that is area, from the right side to the left side. Okay, so then it will becomes Q by A. Okay, then it will becomes Q by A, which is equal to small q. Q by A, which is equal to small q, is called as heat flux. Okay, it's called as heat flux. Heat transfer rate per unit area is called as heat flux. Okay, so Q by A is equal to Q is equal to K multiply by into bracket T1 minus T2 whole divided by L, whole divided by L. Okay, so the all the quantities, that is K, T1, T2 and L, are the given quantities in the problem. So it will be easy to find out the heat transfer rate per unit area or the heat flux. So just put up the given quantities in the equation. So Q is equal to thermal conductivity is provided and it is equal to 387.6. Take that 387.6 multiply by T1 temperature is provided as 100 degrees Celsius. T1 temperature is provided as 100 degrees Celsius. Take T1 as 100 degrees Celsius minus T2 is provided as 0 degrees Celsius temperature. So minus 0, and the thickness of slab, that is L. L is provided equal to 0.25 meter. So take it as it is at 0.25 meter. Okay, and calculate the Q. Calculate the small q, that is heat flux, net heat flux. You can put up your answers in the chat box also for the calculation. Okay, great, great. 155.04. Okay, into 10 raised to 3. Okay, and unit, what will be the unit? Unit for heat flux. Heat flux unit. What is the unit? Watt per meter square. Right, watt per meter square. So our final answer is 1.55 into 10 raised to 5. Okay, watt per meter square. Okay, all the answers are correct one. So you can write down this answer and solve this particular problem. Simple problem as a starter. Okay, over. Shall we move ahead to the next problem? Everyone calculate, do calculation. Is there any problem, any doubt for this problem? Okay, we'll move ahead for the next problem. Okay, so write down problem number two. Problem number two. A reactor's wall, a reactor's wall, a reactor's apostrophe s. A reactor's wall, a reactor's wall, comma, 320 thick, a reactor's wall, comma, 320 thick. So complete thickness of reactor wall is provided and it is equal to 320 Okay. So a reactor's wall 320 thick, 320 thick is made up of is made up of is made up of an inner layer of fire brick, is made up of an inner layer of fire brick in bracket. The fire brick thermal conductivity is provided in bracket. In bracket, K is equal to 0.84. K is equal to 0.84. K is equal to 0.84 watt per meter Kelvin. Watt per meter Kelvin. Watt per meter Kelvin. Bracket complete. Covers with layer of insulation. Covers with layer of insulation. Okay. The reactor wall is made up of fire brick and its thermal conductivity is provided, and this particular reactor wall is once again covered by insulation wall. Okay, is covered with layer of insulation. Is covered with layer of insulation. In bracket, that particular insulation thermal conductivity is provided. In bracket, K is equal to 0.16 watt per meter Kelvin, 0.16 watt per meter Kelvin. Bracket complete, full stop. The reactor operates at the reactor operates at a temperature of the reactor operates at the temperature of 1325 degrees Celsius. The reactor operates at a temperature of 1325 degrees Celsius. 1325 degrees Celsius, and 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 the ambient temperature. Okay, so reactor, consider the nuclear reactor is there, and in that nuclear reactor some reactions are happening, and due to that the temperature released in the nuclear reactor, okay, and that temperature is 1325 degrees Celsius. Okay, now outside that reactor, okay, after the fire brick there is one insulation, and outside that reactor there is a atmosphere. Okay, and that atmosphere having the temperature of 25 degrees Celsius. Okay, and the ambient temperature is 25 degrees Celsius, and the ambient temperature is 25 degrees Celsius. Okay, so determine first one, the thickness of fire brick, the thickness of fire brick, the thickness of fire brick, and insulation, insulation, and insulation, which gives minimum heat loss, which gives minimum heat loss. Second one, calculate the heat loss. Calculate the heat loss. Calculate the heat loss. Presuming, presuming, or pre-assuming, you can say pre-assuming or presuming that the insulating material has a maximum temperature of 1200 degrees Celsius, maximum temperature of 1200 degrees Celsius. Okay, or we have to determine these two unknown quantities. Reactor, we have to consider one reactor, and that reactor working temperature is 1325 degrees Celsius. The complete thickness of reactor wall. Okay, so reactor wall is made up of fire brick and insulating material. Okay, so complete thickness of this particular reactor wall is 320 mm, and the two thermal conductivities of two different materials are provided. Okay, and the temperature, innermost temperature is provided, outermost temperature is provided, and here in the last point they have provided the maximum temperature of insulating material. Here they have provided the maximum temperature of insulating material. Okay, so which temperature is provided? First of all, which temperature is provided? Consider slab A is the fire brick wall, and wall A will be considered as a fire brick wall, and wall B will be considered as a insulating material wall. Okay, so this 1200 degrees Celsius temperature is provided for the insulating material. Okay, and it is the highest temperature for the insulating material. Okay, so where we get the highest temperature for the insulating material? Okay, so that is the question, where we get the highest temperature for the insulating material. So we know that insulating material work, or the main function of the insulating material is to reduce the heat loss to the surrounding. Okay, that is the main function of the insulating material. So obviously the highest temperature will be at the start of that particular wall. This particular highest temperature will be the start of the wall. Okay, so we can say that if you want to draw the diagram, okay, if you want to draw the diagram, so the diagram will be in such a manner. Okay, there are two walls. One is the fire brick wall and another one is the insulating material wall, and the total thickness of reactor wall is provided, and it is equal to 320 mm. Okay, 320 mm. So out of 320 mm, some thickness for the fire brick wall and some thickness for the insulating wall. Okay, so L suffix A is the thickness of fire brick wall we have to consider, and L suffix B is the thickness of insulating wall. Okay, insulating wall. So we have to solve this problem by using the composite wall theory. Okay, by using the composite wall theory. Now inside the temperature of reactor is provided, and it is equal to 1325. Okay, 1325 degrees Celsius. So that temperature will be considered as a innermost wall surface temperature. That temperature will be considered as a innermost wall surface temperature, and so that we are considering T1 is equal to 1325 degrees Celsius temperature. Okay, now the ambient temperature is provided. Okay, so reactor is there, and after that wall is there, and after wall there will be a surrounding temperature the environment is there. So the surrounding temperature is provided as a 25 degrees Celsius temperature. Okay, so that temperature we have to consider for the external temperature of a wall. Okay, that temperature we have to consider for external temperature of wall. Okay, so reactor temperature will be considered as the inner surface temperature of reactor wall, and the ambient temperature will be considered as the external temperature of a reactor wall, external temperature of a reactor wall. And in the last point, it is provided that the maximum temperature of 1200 degrees Celsius. Okay, heat loss permissible, that the insulating material has a maximum temperature of a 1200 degrees Celsius. Okay, so maximum temperature. Now we know that. Now here LB wall is the insulating wall. Okay, so as the heat is flowing, or we can say that as we are moving from this 2 point to the 3 point. Okay, from we are moving through from point 2 to 3. Okay, so this wall will provide the resistance for the heat flow. Okay, so temperature will goes on decreasing. Okay, temperature will goes on decreasing as we are moving from point 2 to 3. So, and in given data it is provided that the maximum temperature of insulating material is 1200 degrees Celsius. So the maximum temperature we will get at the start of that particular wall. Okay, at the start of insulating wall. Okay, so that temperature will be considered as a interference temperature between A and B wall. Okay, and T2 will be equal to 1200 degrees Celsius. T2 will be equal to 1200 degrees Celsius. Okay, and we have to determine what this thickness LA and LB for the minimum heat loss. And next one is the heat transfer rate we have to determine. Okay, these two things we have to determine. So the given data will be in such a manner: T1 is equal to 1325 degrees Celsius, 1325 degrees Celsius. Getting everyone how we have composite this particular problem. Okay, so T1 is equal to 1325 degrees Celsius. T2 is equal to T2 is equal to T2 is equal to 1200 degrees Celsius, 1200 degrees Celsius, and T3 is equal to 25 degrees Celsius. T3 is equal to 25 degrees Celsius. Now, complete thickness of wall, complete reactor wall thickness is provided as a 320 mm. Okay, so in that the thickness of fire brick wall is also there, and the thickness of insulating wall is also there. So addition of these two walls is equal to, addition of these two wall thicknesses will be equal to 320, will be equal to 320. So addition of two wall thicknesses will be equal to 320. So L suffix A plus L suffix B is equal to 320 mm. Okay, is equal to 320 mm. So which is equal to, once again we have converted into a meter, so which is equal to 0.32 meter. Okay, 0.32 meter. And if you want to determine, if you want to convert one of the thickness in another thickness format, then we can say that L suffix B is equal to 0.32 minus L suffix A. Okay, L suffix B is equal to 0.32 minus L suffix A. And the next thing is the thermal conductivity of fire brick wall and the thermal conductivity of insulating wall. Both thermal conductivities are provided as a given data. So K suffix A, so A is the fire brick wall and B is the insulating wall. So K suffix A is equal to 0.84 watt per meter Kelvin, and K suffix B is equal to 0.16 watt per meter Kelvin. Okay, getting everyone how we have composited and we have drawn this particular diagram. Draw the diagram and write down the given data. Draw the diagram and write down the given data. Now further, we know that the total heat transfer through the complete slab is equal to heat transfer through slab A, which is equal to heat transfer through slab B. Means what? जितनी heat complete slab से transfer हो रही है, उतनी heat slab A से transfer हो रही है और उतनी ही heat slab B से transfer हो रही है. Okay? जितनी हीट कंप्लीट स्लैब से स्लैब ए एंड स्लैब बी मिला के ट्रांसफर हो रही है, उतनी ही हीट सिंगल स्लैब ए से सिंगल स्लैब बी से ट्रांसफर हो रही है. ये हमारा मोस्ट इंपॉर्टेंट स्टेटमेंट है, इसलिए कंपोजिट स्लैब के लिए. ओके, सो द हीट ट्रांसफर रेट पर यूनिट एरिया अंडर स्टेडी स्टेट कंडीशन is constant throughout the wall and is same for each slab layer. Write down this statement. The heat transfer rate per unit area under steady state condition, heat transfer rate per unit area Okay, so first our unknown is calculation of or calculation for L suffix A and L suffix B. We have to determine the thicknesses of two walls. Okay, so heat transfer rate per unit area under steady state condition is constant throughout the wall and is same for each slab layer according to this statement. What it means, in a equation format we can write Q is equal to total heat transfer rate throughout the slab, that is nothing but initial temperature minus final temperature whole divided by the total resistance offered by two different slabs. Okay, so T1 minus T3 divided by L suffix A divided by K suffix A multiplied by area plus L suffix B divided by K suffix B multiplied by area, which is equal to heat transfer through slab A. And what is the heat transfer through slab A? It is equal to T1 minus T2 whole divided by L suffix A divided by K suffix A multiplied by area, which is equal to the heat transfer through slab B. And how much it is? T2 minus T3 whole divided by L suffix B divided by K suffix B multiplied by area. L suffix B divided by K suffix B multiplied by area. Okay, so by considering this equation we have to solve the problem. So initially we have considered, okay, now we can transfer, area is the constant one, we can take it as common from this and we can shift on the left side. So the equation will becomes Q divided by A, that is the heat flux, is equal to T1 minus T3 divided by L suffix A divided by K suffix A plus L suffix B divided by K suffix B, which is equal to T1 minus T2 divided by L suffix A divided by K suffix A equal to T2 minus T3 whole divided by L suffix B divided by K suffix B. Okay, so we have to take the two equations out of three equation, any two equation you can consider, okay, and you can solve the problem. So let us consider the first two. Okay, so this one and this one. Okay, so heat flux will be equal to, according to our given data, T1 is equal to 1325 and T3 is 25. Okay, T3 is 25. L the whole divided by L suffix A is the unknown quantity L suffix A divided by K suffix A is the thermal conductivity of A wall or the fire brick, and it is equal to 0.84 plus L suffix B divided by thermal conductivity of B wall or the insulating wall, and it is equal to 0.16, which is equal to T1 minus T2 divided by L suffix A divided by K suffix A. Okay, so we have considered this. So T1 is 1325 minus T2 is 1200 whole divided by L suffix A divided by K suffix A value is 0.84. K suffix A value is 0.84. Getting everyone? Now further, have written. Now next, we have to deduce that equation in a simplest format. So here we have, first of all, what we have done, we have converted this 1 upon 0.84 and 1 upon 0.16. Okay, so 1 divided by 0.84 will be equal to 1.190 multiplied by LA, and 1 divided by 0.16 will be equal to 6.25. Okay, and similar fashion on the left side, 1 divided by 0.84 will be equal to 1.190. Okay, so Q is equal to 1300. Okay, 1325 minus 25, it is equal to 1300, and 1325 minus 1200 will be equal to 125. Okay, so 1300 divided by 1.190 multiplied by L suffix A plus 6.25 multiplied by L suffix B will be equal to 125 divided by 1.190 multiplied by L suffix A. Do calculation whether you are getting the same values or not. Please check. Okay, so if you are getting the same values, then no problem. Okay, so further, once again, what we have done the reduction in this particular equation, 125 divided by 1.190, which will be equal to 105. Okay, which will be equal to 105, and instead of L suffix B, we have considered 0.32 minus L suffix A. 0.32 minus L suffix A. So that we have considered in a given data. Okay, instead of L suffix B, we can convert this L suffix B into L suffix A, so that it will be easy to calculate the thickness. Okay, so L suffix B, here we have discussed L suffix B is equal to 0.32 minus L suffix A. So just we have put up, instead of L suffix B, we have put up 0.32 multiplied by minus L suffix A. Okay, which will be equal to, now here 125 divided by 1.190 will be equal to 105. Okay, will be equal to 105 whole divided by L suffix A. Whole divided by L suffix A. Now this equation totally converted into one unknown. Okay, this equation is totally converted now into one unknown only. So then it will be easy to determine the value of that unknown. Okay, so unknown is L suffix A. So just we have to perform the cross multiplication, or after deducing the equation, we have to perform the cross multiplication. Okay, so deduction will be in such a manner: 1300 divided by 1300 divided by, now 1.190 multiplied by L suffix A and minus 6.25 multiplied by L suffix A. So which will be equal to 5.06 multiplied by L suffix A. Okay, and 2 as it is. Okay, so we will get 1300 whole divided by 2 minus 5.06 multiplied by L suffix A. Okay, we will get 2 minus 5.06 multiplied by L suffix A, which is equal to 105 divided by L suffix A, which is equal to 105 divided by L suffix A. Now the equation is sufficient to do the cross multiplication now. So just do the cross multiplication and find out the unknown L suffix a. Find out the unknown L suffix a. So cross multiplication in such a manner that 1300 multiplied by L suffix a is equal to 105 multiplied by 2 minus 5.06 multiplied by L suffix a. Okay, multiply by L suffix a. Okay, and do the calculation and find out the value of L suffix a. Do the calculation and find out the value of L suffix a. Please let me know the value of L suffix a. And once we will get the value of L suffix a, so it will be easy to calculate L suffix b value, because L suffix b is equal to 0.32 minus L suffix a. L suffix b is equal to 0.32 minus L suffix a. Okay, someone has mentioned the values. L suffix a is equal to 114.5 mm. Okay, right? Whether it is right, please let me know. One more correction. 114, or in meter we will get 0.114 5 or 6. Okay, 5. Okay, 0.1145, and it is in a meter. Okay, this value is in a meter. Getting everyone? Now calculate L suffix b. Okay, so for the calculation of L suffix b, we have to use the given data. L suffix b is equal to 0.32 minus L suffix a. Okay, L suffix b is equal to 0.32 minus L suffix a. Okay, and what it will be? Please let me know your answer. Zero point 205, I think so. 0.205. Whether you are getting the same value? 0.205. And this value is in meter also. If you want to take it in a mm, no problem. Further, you can convert this into mm. And it is in a meter. Okay. Now next, second unknown is we have to determine the heat loss per unit area. Okay, we have to determine the heat loss per unit area. So that is nothing but we have to determine the heat flux. Okay, so heat flux, for the heat flux we have to consider this formula. Okay, so you can consider the complete wall, or you can consider one single wall, and you can apply the Fourier's law for that particular wall. So you will get the answer, no issue. Okay, you will get the similar kind of answer. Okay, so here we have considered the wall A, and we have applied the Fourier's law, or our the heat transfer equation for the wall A. Okay, A number wall, or we can say that the fire brick wall. So the equation for this particular A number wall or the fire brick wall will be for the heat transfer rate per unit area will be Q is equal to T1 minus T2 whole divided by L suffix A divided by K suffix A. Just we have transfer the capital A, that is the area, from the denominator towards this side. So it will be Q by A. That is our the unknown quantity, heat loss per unit area. That is nothing but heat flux. Okay. So T1 we know 1325, and T2 also we know 1200. Here the unknown quantity was L suffix A, and that also we have determined, and it is equal to 0.1146 or 5. Okay, 1146 or 5. Okay, and calculate the Q, that is the heat transfer rate per unit area. Heat transfer rate per unit area, or heat loss per unit area. Okay, 916, 917, 915. Okay, is there any another opinion? So I will write my answer here, and please check your answers. If you have done any mistake, or if you have missed some points, then please do once again. My answer is 916.23, and its unit will be watt per meter square. Okay. Getting everyone? Is there any doubt, any question? Whether you understood or not? Problem, how to solve the problems on a composite wall. So in the next lecture, we'll take two more problems. So that will be better for you. And I will share the PDF copy of this also with you on in your study material. Okay. Hope you understood better. Now we'll stop here. I think 15 minutes, 13 minutes we have consumed of another lecture. Please put up your roll numbers in the chat box, and you can join the another lecture immediately. Remaining student, please leave this meeting and you can join the another lecture.